In this session, I want to talk a little bit about how we can take our ideal gas equation of state and use a little bit of basic physics to get some very interesting information about temperature. All right, in particular, what we're going to look at is the mechanics of gas particles moving through space. So in order to get a handle on that, we need to review a little bit of physics, and in particular there are two elements of physics that we're going to care about, and that is the momentum of particles, which is just equal to their mass times their velocity, and their kinetic energy, which is equal to 1/2 the mass times the velocity squared. So you can see the momentum and the kinetic energy are actually very similar quantities to one another. Now, what I want to do is create a sort of simple hypothetical system out of this. So my simple hypothetical system is going to have two walls, and I'm drawing them edge on here. So these are walls on either side of an enclosure, and my artistic creation here is hopefully clear enough for you. And to start off with, let's just consider one particle. So our one particle's in the middle here, and it's going back and forth. It also can go this way. It's going back and forth in this enclosure, limited by these two walls. Now, we're going to call this the x direction. So our particle is moving back and forth in the x direction. So its momentum will simply be its mass times its velocity in the x direction. Now, we're going to also say that each time this particle hits one of the walls, it's going to bounce off in an elastic fashion, so that it's going to go from having a momentum of mvx to a momentum of minus mvx. So it's a perfectly elastic collision. The only thing that's going to change with this momentum is the direction in which it flows. All right, so what does this tell us about this system? Well, what we're ultimately going to be interested in is how much force does that particle exert on the wall when it hits it. So in other words, the force is somehow got to be related to mass times acceleration. That's Newton's law. But what is acceleration? Acceleration is just the change in time of a velocity. All right, now I could also write this as m times delta v delta t, but to make it even more suggestive, I'll simply say that the mass doesn't change, so I can also write this as the change in mv divided by the change in time. So what we're looking at is force, in fact, is a measure of the change in momentum and in terms of a change in time, or for some small discrete change in time. Now here in the picture that we've drawn here with a particle bouncing back and forth between these two walls, we're going to have a change in momentum. Each time it hits the wall is going to be equal to, so change in momentum in the x direction is simply going to be twice what the momentum is. All right, it went from positive mvx to minus mvx, or if it bounced off the left wall, it went from minus mvx to plus mvx. So every time the particle hits the wall, it's going to change its momentum and change its sign, so it's going to have a total momentum change of 2 times mvx. Now the other question is, how much time does it take to do that? Well, now I've got to add some dimensions to this. I'm going to call this length of distance between the two walls L sub x, L length in the x direction. Later I'm going to need to know what the area of these walls are, so I'm just going to call that area sub yz, because yz are the two directions that are perpendicular to x. And we won't worry too much about what those dimensions are. It turns out it doesn't matter for what we need to do. So the amount of time it's going to take between the times the particle collides with the same wall, that's what I care about, is it's got to travel 2lx. So the distance traveled is 2lx, and the velocity that it's traveling is v sub x. So this is just one of those distance times distance is equal to velocity times time sorts of problems. So if velocity times some change in time is equal to the distance traveled, then I can solve for the change in time as just twice the distance traveled, twice Lx divided by the velocity. So now this gives me a way that I can actually come up with an expression for the force that that particle hits the wall with. So that force for the collision, so I'll make a little bit of a notation there. The force of the collision is going to be the change in the velocity, which is 2 mvx, divided by the change in time, which is 2 lx over vx. So when I flip this around, it's going to be mvx squared divided by lx. All right, so this is going to tell us something about the force that each collision that that particle has with the wall is going to exert. All right, well, one particle is not much of a system, so let's suppose we have n particles. We've got a whole bunch of particles. Now maybe n is a big number like Avogadro's number. So if I have n particles, we're going to say that each of them bounce off the wall and exert the same force. So n particles bouncing off that wall is going to have a cumulative force. So I'll put a little subscript n to mark that, is n particles times m vx squared over lx. All right, pretty easy. But remember, when we talk about the ideal gas law, it's not the force that we care about so much as it is the pressure. And the pressure is given as a force per unit area. So force per unit area. Well, we have an area here. It's the area of that wall. So now if I have all these particles, and let's say those particles are not necessarily all lying on the same line, but they're hitting the wall at random times, the total pressure is going to be this total force, N times mvx squared over lx, and then it's divided by the area of the wall, which we've said is AYZ. So if I make this look a little prettier, it'll be mvx squared over lx times AYZ. But what is lx times AYZ? Well, if we have a perfect rectangular prism here, this thing here is just the volume of my container. So in other words, what I have effectively is that the pressure for this very simple mechanical system is simply given by the number of particles times mvx squared divided by the volume. All right, so what do we make of this? Well, first of all, particles don't move in just one direction. They move in all three directions. So we need to do something with that mv. We need to do something with that v sub x. Well, let's suppose now we've got a group of particles, n particles, that are moving in all the directions. All right, so they've got an x component, they've got a y component, and they've got a z component. Well, one thing we know for sure is that if we were to look at the square of the magnitude of the velocity squared, if these are Cartesian directions, then it must be equal to vx squared plus vy squared plus vz squared. Now, we're going to assume that this system has a property we call isotropic. That is to say, it doesn't prefer one direction over another. So it's equally probable to be moving in any kind of direction. So that means that each of these, on an average basis, is going to be about the same. So on average, they are the same. So now if I care about the average square velocity, that's going to be equal to the average square x velocity plus the average square y velocity plus the average square z velocity. But all of these are the same, so I can just say that's equal to 3 times the average of the x velocity squared. Or better yet, I can specify that the x velocity squared on average is just equal to 1/3 of the total velocity squared. All right, let's get to a new page so that we can follow this through one step further. So just to remind you, what we have at this point is that pressure is equal to the total number of particles times mvx squared over volume, but we've just shown that this mvx squared can be written as m times v squared average divided by 3, and then we've got to divide by the volume. Don't get the two V's confused. I'll try to draw the volume V a little bit bigger so it looks more important. All right, so we've got this sort of relationship, but I'll also note, remember we said that the kinetic energy of these particles, and I'll write that as E sub kin, is 1/2 mv squared. All right, but if I'm talking about the average kinetic energy, then I can write this as 1/2. They'll all have the same mass, so it's just 1/2 this. And I know that this v squared is actually 3 times vx squared, but whatever we want to use here, we can look at this mv squared is equal to twice the average kinetic energy. So now if I substitute this in to the upstairs of this fraction, I'll have that pressure is equal to N times the average of the kinetic energy times 2 divided by 3 times the volume. Well, this is looking kind of suggestive. If I multiply both sides by volume, I'm going to find that pressure times volume is equal to 2/3 the number of particles times the average kinetic energy of those particles. Okay, or another way to look at this is if I want to convert this into the number of moles times Avogadro's number, and then say that Avogadro's number times the average kinetic energy per molecule is going to be some sort of average kinetic energy per mole, then I can rewrite this equation down here as PV is equal to 2/3 times the number of moles times the average kinetic energy per mole. But I also know from the ideal gas equation of state that PV is equal to the number of moles times RT. So if I substitute this, and I'll do this in red, if I substitute this in here for PV, I will end up having an equation that says that little n RT is equal to 2/3 little n times average kinetic energy per mole. And oh, well, these numbers of moles drop out. Let's multiply both sides by 3/2. I learn that the average kinetic energy for a mole of these gas particles in an ideal gas is just 3/2 times the gas constant times temperature. Wow, what does that mean? Does it have any significance? Well, think of this in terms of, this is a statement about the mechanical energy or the kinetic energy of the particles, and this is the only variable on the right-hand side of this equation is the temperature. So you can think of this as a way of defining what temperature means. When temperature increases, what you're increasing is the average kinetic energy of the particles in a system. This is a really important fundamental relationship, and it tells us that when things get hotter, it means they're moving faster. And when things get colder, it means they're moving less fast, they're moving slower. And this is a fundamental relationship that will help guide us in terms of how we think about temperature as a fundamental property of systems. Note also that we've associated temperature changes with flow of heat. So in this case, what it means is the flow of heat just means that kinetic energy went from one place to another. Something that was cold, if it got hotter, it increased in its kinetic energy. If something hot got cooler, it decreased in its kinetic energy. And so this whole issue of thermal equilibrium is really one that's about somehow equilibrating the kinetic energies of the two parts of systems that are interacting. So I hope this made sense, and I hope this enlivens your understanding of what's going on in this particular lesson.